point, we're going to leave the topic of the Partnership for Safe Water, and I'm going to pass it on to Andy Seidel to talk a little bit more about options for controlling chloramine concentration in the distribution system. Andy?
Thank you, Barb. So let's back up a little bit and let's talk about the chloramine chemistry itself. As Barb mentioned, chloramines are the chemical species formed by the reaction of ammonia with chlorine, and they've been used successfully for decades as water disinfectants. And again, as Barb mentioned, primarily for two reasons. One is that there's a low propensity for these chloramines to create disinfection byproducts, or DBPs, and really because as an oxidant, they're much less aggressive than free chlorine. And secondly, they have persistence or longevity. They just last longer in distribution systems. So that really, those are the real reasons those chloramines have been used for so long and so effectively. If we go to the next slide, we can look at the formation of the three primary chloramine species, only one of which, monochloramine, the first equation, is desirable in a water system. These other variants, dichloramine and trichloramine, they have a number of side effects, such as limited persistence or life in a distribution system, objectionable taste and odor issues. So these are essentially, these last two are unsuitable for drinking water and generally not a beneficial byproduct of the chloramine chemistry. Most importantly, if you look at the first equation where we form monochloramine by reacting ammonia with hypochlorous acid or chlorine, you can see that the reversible nature of that reaction means that monochloramine can actually decay. It's called monochloramine decay, the phenomenon where essentially the monochloramine through a hydrolysis reaction can create ammonia back in the system again. So this is one of the reasons why perfectly good chloraminated water can leave from a water wholesaler treatment system and arrive at a customer tank or reservoir and have some level of ammonia already in it. It's not necessarily that the water was bad, it's just the nature of the reversible chemical equation. So if we go to the next slide, we can see that chloramines are effective and persistent as a disinfectant, but the reversible nature of that chloramine creation can create problems, and certainly, as Barb mentioned, one of the major issues is nitrification. This is really something the EPA has examined, and the EPA study there was an EPA-cited study which found that 63% of chloramine-utilizing utilities had some degree of nitrification in their systems. So you really have two competing issues. One is that excess ammonia in a distribution system can be sequentially oxidized by naturally occurring bacteria. You may have heard of AOBs or NOBs, which convert the ammonia to nitrates and nitrites and then to nitrates, and both of those can have public health ramifications. On the other hand, excess chlorination to prevent nitrification can lead to levels of undesirable di- and trichloramine. So utility operators are confronted with this challenge of being on the knife's edge of either having excess ammonia in their system or excess chlorination, both of which can have undesirable effects on the quality of water. And therefore, many utility operators are forced into convoluted operational strategies that include excessive tank cycling, chlorine burns, and tank dumps, which are increasingly frowned upon, certainly in water-scarce areas in the western United States. And they do these things to manage nitrification risk as well as taste and odor issues. Next slide, please. So if we look at the chloramine breakpoint curve, the essence or the most important factor in controlling chloramine residuals in a distribution system, in a reservoir tank system, or the distribution system as a whole, is understanding where the residual is on that chloramine breakpoint curve. So if we look at the curve, we can see that the y-axis on the left expresses the chlorine residual in the reservoir. Let's assume this is a hypothetical tank. And the x-axis on the bottom expresses the weight ratio of chlorine to ammonia, or essentially the dose of chlorine that's added to ammonia-containing water. The breakpoint curve itself expresses the chloramine residual in a tank, with the yellow star in the diagram really representing the ideal residual set point, or as Clifford White in his seminal Handbook on Disinfection referred it to as the hump. So if you look at that sort of residual hump value, and on either side of that value at that local maximum, you're either going to be on the right side or the left point of the breakpoint curve if you're below the optimal value. So therefore, if you have a residual that's less than optimal, you're on one side of the curve or the other. If you look at that left side, there is an excess of ammonia in the tank, and it's remedied simply by adding a little bit of chlorine. You can start to climb the curve and increase the residual until you reach the maximum, which is that yellow star or the set point. If you find yourself on the right side of the curve, there's a scarcity of ammonia. So by adding chlorine, the monochloramine residual will actually be reduced as the existing monochloramine is destroyed by this highly oxidative environment. So in other words, if you were on the right side of the curve and you added more chlorine, it wouldn't be unusual because there is a scarcity of ammonia to start to see the residual actually drop. And if you continue to do that, you actually get to the break point, which is at minimum on the right side of the curve. So ultimately what you're essentially doing, because the oxidative environment is so aggressive, you're actually oxidizing the ammonia to nitrogen, and chlorine is actually being reduced to chloride. So you're really having a very little residual at that minimum. And then if you add more chlorine, of course, you start to climb up, and you're in the free chlorination zone on the very far right of the slide. Next slide, please. So understanding where you are on the breakpoint curve is critical, and then there are really four criteria that are important to control your chloramine once you know where you are on that breakpoint curve. So if you know where you are, then you have to accurately dose the reagents, which are ammonia and chlorine, or sometimes just chlorine, and control the ratio very accurately between the two reactants. Secondly, the tank has to be completely mixed to eliminate any chemical stratification and ensure that the analytical readings of residual reflect the condition of the entire tank versus pockets of unreacted or improperly reacted chemicals. So if you have a tank that's not completely mixed or not in equilibrium, you're going to have pockets of residual or pockets of unreacted chemicals that can improperly indicate a condition that isn't representative of the entire tank. The third issue is really you need to have a method of introducing the two chemicals, chlorine and ammonia, in a very aggressive manner so that the ammonia introduced is consumed by the kinetic collision of chlorine in the tank. It doesn't help to introduce ammonia in an area of the tank or chlorine in an area of the tank and not have the two molecules meet. You want to be able to have that introduction in a very aggressive, high-energy kinetic way so that you can actually form monochloramine immediately. And then finally, you have to have control logic and instrumentation that will allow you to be able to react very quickly to changing dynamics as that tank sees new water or is cycled through its normal fill cycle. Next slide, please. So this is our monochlor system. We've got about 50 chemical management sites in operation with an equal amount in design right now. It very simply and elegantly manages the chloramine residual levels in tanks and reservoirs. If we look at the simplified PFD in the slide, we start on the left side. As our chlorine source, we like to use an on-site hypochlorite generator, the microchlor system, which generates a fixed amount of sodium hypochlorite at 0.8%. And this really eliminates sort of the guessing that can occur in terms of the chlorine, active chlorine amount, for example, with bulk hypochlorite, where you have a certain amount of degradation that occurs, particularly in summer months. So we know exactly the amount of chlorine that we're able to react in our system, and it's going to be constantly at the 0.8%, which the generator creates. Secondly, as we move to the center of the graphic, we use a ammonia source in the form of ammonium sulfate salt solution. We find that that's the safest and most stable form of ammonia for this type of use. And then finally, on the far right, the tank shark eductor mixing system is used to do two things. One, provide a very high energy reagent introduction and mixing, as well as keep the entire reservoir in equilibrium so that we're dealing with a fully mixed tank. And we know that when we're sampling that tank, that sample point reflects the entire chemistry of that tank. So the combination of sort of powerful analytics, reliable reactants, and power really allow the monochlor system to be agile enough to manage the changing environment of the water reservoir. Next slide, please. So as we look at a hypothetical tank in action here, we can really see a couple things going on. First, this is a case where the operator observes, or the system observes, essentially that we have a residual in the tank that's below the set point. We happen to be on the left side of the curve, which, if you remember, that's an area where we have a little bit of excess ammonia. The system detects a drop in chloramine residual as the tank chemistry resides on the left side, and essentially the monochlor system adds chlorine in the form of sodium hypochlorite at 0.8%, and the residual climbs until it reaches that set point with the yellow star, or that hump. The free ammonia on the right side of the graphic, you can see that the free ammonia that was existing in excess on the left side of the curve is basically consumed through that process as you reach that residual set point. So if we go to the next slide, we can see that we have a different situation. Again, we have a residual which is below the set point. In this case, we're on the scarce ammonia side of the curve, where there's not a lot of ammonia. There is no ammonia essentially left to react. And if we add chlorine at this point, we drive the residual down further. So if you look on the right side of the graphic, you can see that we initially add chlorine. We notice that the residual drops further, as depicted by the green line, which indicates that we are in fact on the right side of the curve. So what we do with the monochlor is the monochlor starts to add automatically the correct ratio of chlorine to ammonia because we're on that scarce ammonia side of the curve, and the residual climbs up that curve to that set point. So that's really how the monochlor system works. What I'm going to have Brent Simmons do is now explain sort of how the system is constructed and how it's actually implemented in two very quick examples of how it works, and we'll move into the utility case studies. Brent?
Next slide, please. Okay, what you're looking at here on the upper left is a monochlor pilot trailer. Bottom left is a picture of what's inside of that pilot system, which consists of the on-site hypochlorite generation system. And by the way, the PLC-based control for the on-site system is also where the algorithm that Andy just described lives. That's where the calculations are made, and that PLC panel not only supervises the generation of on-site hypochlorite, but the entire process is monitored at that location, and that's the operator interface. But you see bottom right, the side view of the chlorine generation system, supply of salt. To the right, DI bottle, because we don't have a disposal mechanism for a softening system in the field. And then the trailer is fitted out with the hypochlorite storage tanks, double containment, metering pumps, analyzers, a little bit of a lab space. The fully contained, fully functional pilot, which can be deployed and put in operation in about 2 days. So we have these running around the country right now, and some very successful results you'll see coming up in the following case studies. Next slide, please. This is San Jose Water. Typical installation detail. We have anywhere from 2 to 4 penetrations, generally through the hatch flange, that are made in a sanitary fashion. You see the tank shark mixer being deployed on the upper left. It's all NSF approved materials of construction, and it's being sanitized before it drops into the hatch. There is no confined space entry, no divers required. Everything about the system simply drops through the hatch and is lowered down to the base of the reservoir. Slide on the right is this particular regulator. We had a requirement to keep the liquid ammonium sulfate 30 feet away from the chlorine generation system. So a little yellow plastic cut there is where the LAS was stored and fed from. And just as a comment, if any of you have worked with the aqueous ammonia feedstocks, you can imagine the nightmare it would have been, in summertime, 100 degrees, trying to maintain that liquid, where the liquid ammonium sulfate is completely stable, zero volatilization, and much friendlier from an operator perspective. So very successful deployment at San Jose Water. Next slide, please. More detail of how we actually interfaced to the reservoirs or tanks. This was a brand new reservoir, which actually had welded fittings to make the penetrations, just a little different variant. We have probably 15 different versions of the tank shark itself. The one on the right there is set up for the injection of gas chlorine, which the monochlor process supports. You see a PVC bonnet located above a mixing nozzle, 2 additional nozzles, and this particular unit was going into an old tank where we only had a 24-inch square opening to work with. So it's been built with a collapsible base. That was deployed in Texas about 2 years ago. Next slide, please. This is the actual 1 million gallon tank that we deployed the tank shark at San Jose. It's approximately a 40-foot tall tank, and you're looking at the liquid level about 10 feet down from the hatch. So you see the amount and the high energy mixing of that water. So you're seeing the effect from the tank shark 30 feet below. And a very important part of the whole monochlor deployment is the amount of applied mixing energy. This obviously is showing you we're getting good mixing, but every product that goes out, we look at the reservoir geometry, the reservoir volume, and the dwell time in the reservoir to determine the amount of energy we need to apply. And as an example, our smallest mixer or tank shark is in the neighborhood of 1,000 watts of applied mixing energy. Our largest systems go up to 15,000 watts. So very, very important, like Andy mentioned, that you have the proper amount of energy being applied to be successful in the monochlor approach. Next slide, please. Some data from East Bay Mud in Northern California. This is all detailed in an OpFlow article also, but the 6 months worth of data you see here, we had a reservoir, 10 million gallons, constant issues with low residual, and we deployed the monochlor process, and you look at the data over the course of 6 months, a couple spikes relating to analyzer calibration, but basically solved the problem by implementing the 4 major aspects of monochlor, and this would be one of our largest mixers due to the volume of the reservoir. Next slide, please. More data from Eastern Municipal. You see they raised the set point to 3 parts per million, and the yellow line, we're actually tracking tank elevation, which moves around from 10 to 23 feet on that 10 million gallon reservoir. And you can see we have no effect, or there's no effect upon the residual associated with tank levels. So the monochlor process and tank shark works independently of fill cycles in the reservoir, draining of the reservoir, and overall level. It diagnoses the internal quality of the reservoir and doses appropriately to maintain set point. And this is my last slide. We're going to hand it over to Francois from San Jose Water. Next slide, please.
Thank you, Brent. This is Francois with San Jose Water Company. I'll just give you a little background before I cover the details of this slide. San Jose Water Company is actually celebrating its 150th anniversary this year, which is good for the West. I'm sure there are some Eastern utilities that think it's a young utility. We serve a population of about 1 million customers in the South Bay of San Francisco. We have about 2,400 miles of pipe, 25 well fields, 2 water treatment plants, and we import surface treated water from the Santa Clara Valley Water District from 14 different turnouts. We have 26 basins, typically earth embankment type of reservoirs, and 71 distribution system tanks. And we monitor our samples for the TCR and for growing disinfections at 140 distribution system sample taps. Water, generally speaking, is 50% chloraminated. That's the water we purchase from the Santa Clara Valley Water District. And the other 50% comes from groundwater and the water that we treat at our own treatment plant. So that sounds like this 50-50 mix is a recipe for disaster when it comes to nitrification, and that would be definitely correct. However, I should say that we typically segregate those sources of water in different pressure zones, and we certainly operate our system to minimize mixing of those two different water. We also have plans to alleviate this issue by converting our larger water treatment plant to chloramine early next year, and the major ground water station also to chloramine, where they typically mix or pump water to chloraminated zones. In 2011, we kind of went through an update of our nitrification plan and really came fairly quickly to the conclusion that our chlorine residual management really needed some improvements. And we really didn't have the tools to do a thorough study and to assess our performance. And that's when we became familiar with the optimization of the distribution system program, and we joined the program in 2012. Our initial assessment clearly confirmed that we needed to improve our performance related to chlorine residuals. We also found, incidentally, that our pressure monitoring and data and reporting was probably could help some improvements, and we've addressed that, and that should actually be complete this year. And in terms of main leaks, we actually already have an optimized system where we have been blessed to have had a fairly aggressive main replacement program for now many years, and so we're performing well in that sense. On that slide, you can see the results for our chlorine residuals. I should point out that we are meeting regulations in the sense that we have detectable chlorine residuals in all of our sampling points. Having said that, though, that's the difference between meeting regulations and actually having an optimized system. The partnership gives targets that Barb went over. For free chlorine is greater or equal than 0.2, and total chlorine, read that as chloramine, as greater or equal to 0.5. Initially, we were pretty much doing compliance monitoring, which was our TCR samples, and we have improved that, where we've included our tanks, where we monitor all of our tanks on a weekly basis. And you can see that the actual measurements fall short of the 95% of the monthly routine measurements. In the TCR samples, we do slightly better, greater than 80% on our samples. In the tank and reservoirs, we hover around 50%. I should really point out that, in my opinion, actually, even if meeting the partnership's residual goals, you probably don't have an optimized system, in a sense that chlorine residuals for monochloramine of 0.5 or less than 1 typically are subject to rapid nitrifications in tank and depending on the circumstances. And we have found, and other utilities have found empirically, that probably greater than 1.5 is the only way to ensure that one can stave off biological activity and potential rapid nitrification, which then would lead to depleted residuals. So how do we do that? And that's where the partnership helped us. Our measurements and our data, our analysis of the data helped us understand that we could not possibly improve our residual through our distribution system without addressing the tanks. The old technique, when there was a crisis or coliform positives showed up in a particular location, would be the hatch and dump technique, where an operator would climb the tank, open the hatch, and pour some bleach. And as you well know, that's not really effective, and sometimes it actually does more harm than good. So we looked for solutions and originally tried and actually built some portable mixers that the operators could deploy to tanks, and then they would try to boost the residual, but that we found that to be very time-consuming. We didn't have the right mixing energies, and we had to abandon that effort because really we were just not successful at it. That's when we decided that if we could have an automated boosting system at key locations, that perhaps then we could just raise our residuals in those key locations that suffered from nitrification and keep the residual up and hopefully benefit downstream tanks or reservoirs. Next slide, please. So this is the results for our first pilot, which was done in 2014. Roughly speaking, a 3-month pilot. And Brent already actually kind of showed you what the system was like. As you can see, we very rapidly went to the initial set point, which we decided was too low, really. And we had a new set point around 2.5, and we were able to maintain that. There were calibration issues and so forth, and those spikes are kind of part of the troubleshooting. More interestingly, the purple line below it is Crothers tank, which is downstream of Alum Rock, and really that was the purpose of our pilot. We didn't think that it would be difficult to boost one tank, but we really cannot afford and didn't want to get in the business of boosting every one of our tanks. So we wanted to see if boosting one tank then could benefit tanks downstream, and that we found that after some chlorine burn and cleaning and sustained level of chlorine in Alum Rock, that the tank downstream of it, Crothers, started to turn over and showed decent chlorine residuals. Now, we had a power outage at the station due to work being performed there, and the pilot was interrupted, and you can see that the residual crashed very rapidly. So I think it drives the point that this is not a one-time deal. You have to have an ongoing boosting, and once you stop doing that, you pretty much revert very quickly to where you were in the first place. So based on this data, we were very encouraged. We decided to go ahead and do a permanent installation at actually a reservoir upstream from that, which was a more complex set of reservoirs. Next slide, please. And that's our Miguelito tanks. It's actually 2 basins, earth embankment basins. They are 4 million gallons each. And so our system there actually monitors and boosts each of the basins independently of one another. Depending on how the system uses the water, it's possible that one reservoir would need more chlorine than the other, and the system handles that very well. As you can see, prior to the installation early this year, the chlorine residuals there in all at all 3 locations were really not adequate. While detectable, again, they're not high enough to stave off nitrification and to maintain good residuals through the distribution system. Once we turned the system on, and we had a set target of 3, eventually we crept up to 3, everything fell into place. both basin and the downstream tank of Alum Rock, and then Crothers responded very well and started to show very good residuals. I should point out that there is some wide fluctuation, as I am sure you have noticed, where the chlorine goes from 2 something to less than 2 to and so forth. And that seesaw is just really kind of operational issues that we had to work through in a sense that our operators had never dealt with a system like that. Typically, they would do measurement, they may do an intervention, but they were not in the habit of maintaining boosting system with all the implications, the maintenance that is required. So one has to keep the system stocked with salt to generate the chlorine. One needs to make sure that there is LAS available. The probes need to be calibrated, pumps need to be maintained, and so forth. So we had to go through working out all those kinks, ensuring that our delivery would show up on time, that the operator would place the orders at the right time, and so forth. So now we are at the point where the system is very stable, and both basins at Miguelito and the 2 downstream tanks actually are doing very well. So I think we consider this a success, and as a result, next slide, please. We will be looking at doing further investments in our distribution system with the goal to get to a point where all of our tanks and our residuals throughout the system meet certainly the partnership criteria, but possibly better than that. We have planned capital improvement. The partnership, again, helped us understand issues. We've taken care of all the low-hanging fruits, taken tanks out of service, and so forth. We have discovered that some of our tanks in a zone, if one of them is hydraulically lower, and depending on demand, one of them doesn't really turn over. So we are installing SCADA control valves so we can separate, essentially split the zone during times of low demand, and those tanks can work independently from each other. We are installing additional residual boosting systems at key locations, and we are conducting a study throughout our system by testing every tank and building chlorine decay curves so we can understand where we need to boost and minimize the number of boosting stations, but at the end of the day, making sure that all of our tanks have appropriate residuals. We also have worked with UGSI to develop a water quality station or cabinet, and that essentially will be installed in 10 of our tanks this year. The cabinets are essentially interfaced with a mixing system and then provide a chlorine residual that is relayed to our SCADA system, but more importantly, provide the operators with an ability to introduce chlorine and or ammonia to the tanks or reservoir in a very easy fashion, and so that we're really excited about being able to actually do spot boosting at places that will not have boosting, but for whatever reason there's something happened, or we have a need to increase residual in a specific area of the distribution system. We will be able to do that without climbing tanks, without opening hatches, or without having to install a boosting system. And as I mentioned, 2 of our well fields will be switched over to chloramination this and next year, actually, and one of our filter plants will be online as well with chloramine early next year as well. We, again, use the partnerships guidance and self-assessment criteria, and the fact that we have to do annual report, which is very important because I think it forces us to look at our data to see if we have made any progress and to see what else needs to be done in order for us to get where we need to go. So we have improved our SOPs for tank dosing, inspection, cleaning, and then we will use a lot of data generated by the partnership and the monitoring and the real-time monitoring to provide that data to our planning department, which will incorporate that data into the hydraulic model and be able to give us water age and disinfectant residuals data as well. And with that, I will go ahead and turn over the presentation to Tom, and thank you for your time.
Thank you, Francois. My name is Tom Caulfield. I work in southeastern Pennsylvania for Aqua Pennsylvania, subsidiary of Aqua America. The tank that we're focusing on right now is what we call Hillside Tank, with 12 million gallons worth of storage on site. It's essentially a critical tank in the area that you're seeing on your screen in our Eastern Division. A little background on Aqua Pennsylvania. We serve in the area of 950,000 customers in southeastern Pennsylvania through over 5,000 miles of pipe. We have 7 different surface water treatment plants, 70 remote well stations, and upwards of 40 different tank locations with varying storage capacities. Hillside Tank is one of the few 10 to 12 million gallon tanks that we have. So it's a very large tank, and like I said before, it's a critical tank in this area. It affects all the tanks in the surrounding area. So each summer, and if you operate a system, you've heard this before, but whenever it starts to get warmer, or if it's already warm when it gets hotter, we start to see the residual decline in this tank consistently anywhere between June, July through the end of September, beginning of October. This past September in 2015, we saw a severely challenged residual at Hillside Tank. We had a detectable residual, but it was very low. And we decided to deploy the monochlor pilot trailer in order to see if we could mitigate that issue. Our goals were to maintain a set point residual, to see what the impact of maintaining a residual at Hillside Tank would have on the surrounding area, and see how it would impact our operating costs that would go along with if you were to chlorinate a tank. Another challenging aspect of Hillside is because it's in the middle of this particular division, it receives water from 4 different sources. 3 of them are surface water, 1 of them is groundwater, and all of them have different varying levels of monochloramine and free ammonia that combine into one storage tank to form varying levels of chemistry, as Andy had mentioned before. So we were looking for a way to solve this issue, maintain a residual, and have a mixed tank. Now, we did have a mixing system in this tank, so the tank was mixed, but we were still having a severe problem with maintaining a minimum residual effectively. Next slide, please. So we ran the pilot for approximately 2 months. We installed it in the first week of September. It was not an easy process because of the height of this tank. This is a 120-foot tank. The operational level is between 80 and 100 feet inside the tank. After running the system for about a week, we did not see any significant change in the residual inside the tank, basically because we already had a demand event inside the tank. The tank was already essentially gone, as we'd like to call it, or severely challenged with its residual. So the decision was made to breakpoint the tank. And it's an interesting point to note here is that we were actually able to utilize the monochlor pilot trailer equipment in order to more effectively chlorinate the tank than traditional methods, either injecting into the fill line into the tank, or as Francois had mentioned, you climb the tank, dump a carboy in, and so forth and so on. So we were able to utilize the monochlor trailer equipment in order to safely and effectively breakpoint a 12 million gallon storage tank relatively quickly. After about 4 days, the residuals did climb from around a half a part to 1.5 parts per million. And that set point was maintained through the rest of the pilot. Next slide, please. Next slide, please. Okay, thank you. Now, at Hillside Tank, because of its positioning within in the division, it is a centrally located tank. So you do see significant flow rates into and out of this tank based on the fill-draw cycle. Now, interestingly for this tank, it has a different fill and draw cycle than most, I would say most tanks, at least in our area, maybe not the rest of the country, but typically most of our tanks fill during the nighttime when there's low demand, and they draw down during the day. It was actually reversed for this tank, where it would fill during the day and draw down during the night. That did factor into our analysis as far as how to approach solving this issue. You can see by these graphs, it indicates where the chemical feed was turned on after the system was in place. You can see the spike in the upper left-hand graph, you can see the spike where we took action to breakpoint the tank utilizing the microfloor system. In the graph to the right, upper right-hand side, you can see where the residual slowly climbed to our 1.5 milligram per liter set point, and then was maintained for the remainder of the pilot. The flow rates for this tank could be in excess of 2,000 gallons per minute, both filling and draining. So it did see significant swings in tank elevation. Even though it was only 20 feet, it could be rapid. But the microfloor system was able to adjust to that and maintain the 1.5 milligram per liter set point. For these graphs in particular, I do have to thank Carolyn Hathaway from Aqua PA. She was able to put these together and basically process all of the data that we gathered from this pilot, so I did want to thank her for that. Next slide, please. So these are some of the lessons learned after the pilot. This was a challenging tank to address because of the size and the effect it would have on the surrounding area, as well as the number and difference in makeup of the sources of water for the tank. The pilot was a 40-pound per day system. In hindsight, which is always 20/20, we probably could have used a larger size, but with the size that was provided on site, we were able to accomplish a lot with this tank. We did see a positive effect on 4 surrounding tanks in that division, where before we were having issues with the residual being very low at Hillside, we would see a negative effect where the residuals would decline and or bottom out, which would require us to chlorinate the tank. After the residual was maintained at Hillside at 1.5, we did see upswings in the consistent residual at other tanks in the area, 4 other tanks totaling about 9 million gallons of additional storage. The water quality distribution system also increased with the residual increasing in a consistent manner, and we were able to see that through our total coliform rule sampling and distribution sampling in the area. This is a quick and dirty number for operating cost savings. This is only including labor and chemical costs for that site, for Hillside, to chlorinate that tank. Per chlorination, I estimate between $2,000 and $3,000 per chlorination. We could expect to do that several times during the summer, and that's just for that tank site. That's not including any valve operations that need to happen, systemic issues in the system that need to get changed because of the outage of that 12 million gallon tank. That I haven't even begun to try and calculate. That's going to be handed off to our accounting department. One of the most significant things that I saw from this pilot was once the tank was break pointed, it was isolated to allow that free chlorine residual to work on the demand inside the tank that we attributed to the AOB bacteria. We did see a consistent increase in the residual during that isolation, and then the tank was able to maintain that 1.5 milligram per liter set point throughout the rest of the pilot. And the important thing that I took away from it was being able to manage a tank, a critical tank, in a densely populated area with varying levels of monochloramine and free ammonia coming from several different sources that could change at any given hour based on hydraulics, system demand, or operational issues at any one of those filtration plants. And being able to manage that and basically increase the water quality for an entire area of your system, and it's automated. So, once you're able to dial in what you need, the system basically just coasts along on its own, and that really helps us be able to maintain the water quality in that area and eliminate an operational problem so that I can go focus on something else that requires attention that would benefit the system as well. So at this point, I'll hand it back off to Andy.
All right, thank you, Tom. Next slide, please. To recap, while the chloramine chemistry is certainly complex, the management of chloramine residuals doesn't really have to be that complicated. If you take care of adding enough mixing and motive energy to get a tank homogeneous from a chemistry standpoint, it becomes easier. Certainly having an energetic mixing zone where you can have that kinetic collision of the reactants, ammonia and chlorine, and create chloramines at will, that certainly is helpful and a requirement. If you can install real-time sampling to accurately assess the actual chemistry within that homogeneous tank, very, very critical. And then an algorithm which allows you to assess where you are and add the right ratio of reactants at the right time to maintain that reservoir. Those are really the four critical items. And the benefit, obviously, is that your operational staff will have time to increasingly add value in other areas because your residual will be maintained. There'll probably be less cycling of those tanks because you're going to, and essentially you'll be able to utilize your capital more fully in terms of your capital in your reservoir and tank system. And then finally, this all gets done with our monochlor system. It gets done without the need of having mechanical parts or mechanical movement inside of the tank or reservoir itself, which makes maintenance and long-term performance much more easily attained. Next slide, please. So I want to thank everybody for participating. First of all, AWWA and the Partnership for Safe Water. Barb, thank you very much. And certainly Aqua America, Tom, and San Jose Water, thank you so much for being great partners and being able to take the time to talk about your chloramine residual management challenges and solutions. So Barb, at this point, I'll turn it over to you. I think we might have some time for questions.
Yeah, I know it's past the top of the hour, and I appreciate everybody for hanging on, and I'll just second Andy's thanks to the webinar attendees and to today's speakers. We do have a few questions, so we'll go ahead and take maybe another 5 minutes for questions, and feel free to hang on if you can. The first question says, how do you prevent freezing of the chemical feed lines and sampling lines when they're exposed on top of the tank?
Depending on the environment, you would typically insulate and heat tape going up the side of the reservoir. This really depends on where you are. We have a number of systems up in Utah, Wyoming, which it's just a bit of engineering, but it's definitely doable.
Excellent. Thank you. This next question is directed specifically to Francois, and the question is, how did you determine that nitrification was the primary factor for the low residuals?
Yeah, so we essentially have looked at incoming water into tanks and tanks with even as good of a 24-hour turnover. We had some situation where we had clearly 1 ppm or greater coming in and 0 or just barely detectable coming out. What we have discovered is that tank cleaning, particularly a thorough cleaning, even chemical cleaning, will help and will boost those residuals, but they're not really sustainable. And so we have deducted that clearly the biofilm in the tank and the biological activity was responsible for the degradation of the residuals.
Great, thank you. And I think we'll do one final question. This really goes to Francois and Tom. Aside from the water quality improvements themselves, did you see any operational types of savings for implementing the system?
I will let Tom answer.
So the way that I look at it is that this system basically took away a major problem that I had to deal with consistently every season. So moving forward, I essentially don't have to worry about hillside tank anymore, other than making sure that the residuals are okay in the system like we normally do, but the consistent chlorination and then waiting, and then we had to chlorinate again, and then waiting again, and then hoping that it would stop. That aspect of it has gone away. I don't have to worry about that as an operator. As far as cost-wise, my estimate locally for our labor force, having personnel on site, the time it took to do it, the application of chemicals, just locally, we estimated between $2,000 and $3,000 spent per chlorination. And like I said before, that's very conservative. That's not taking into account changes made out in the distribution system because you're going to need to take the tank out of service, or any other systemic issues that would result from that. I didn't include any other sampling, additional sampling, flushing costs, valve operation costs, anything like that. I mean, operational cost savings besides the chlorination of the tank, flushing would probably not have to be done as often because your residuals are maintained. It would, if it impacts your system as much as it did my region, those other 4 tanks maybe don't have to get chlorinated, and the pipe in between those tanks, maybe you aren't suffering from as much nitrification as maybe you were before. So it can have a very large impact on a very large area depending on the hydraulics and the size and implication of what that tank affects.
Wonderful. Thank you, Tom, for that explanation. That's all the questions we have time for. And one additional AWWA resource I would direct listeners towards is M56, which is the Nitrification Prevention and Control Manual in Drinking Water that's published by AWWA that can provide some additional insights into the complex world of chloramination and nitrification chemistry. So thank you again for everybody for attending, and also thanks to today's speakers. That concludes the webinar.